All right, derivatives of a composite function. So I've written a little bit of a definition here because technically it needs to be written. If f and g are functions that have derivatives, then the composite function h at x, which is made up of the function g at x inside the function f, the derivative of that function, so h prime x, would be the derivative of the outside function, which is our function f, with the original function g inside of it, multiplied by the derivative of function g. Okay? This is very similar to the power of a function rule. Okay? The only difference is it doesn't have to just apply to a exponent type question. Okay? So we're going to go through this. We'll go through a couple examples. The very first example we're going to go through is actually the second example in your textbook. So, example 2 in your textbook. They've given us h at x is equal to x squared plus x over 3 over 2. Okay. What I'm going to do in this question is I'm actually going to break this into two separate variables just so questions 3 and 4 make a little more sense. Now technically we can just use our power of a function rule here. I want you guys to realize that, for instance, if I were to put let y equal x squared plus x, this question would now become h at x is equal to y 3 over 2. Okay? It's very simple to solve this part. Okay? So in other words, you could almost say that function y is our f at x in this case. And our g at x is the x squared plus x part. Okay? So the, the f at x is the, I meant to write it below. This is the f at x of our function. Okay? So this way we can see this as two separate functions now. The x squared plus x as our g at x, and the y to the power of 3 over 2, or the 3 over 2 as our f at x. So according to our chain rule, what we need to do to solve this for h prime x, we need to take the derivative of the original outside function, f at x, with the g at x inside, multiplied by g prime x. Okay? So, what that means is, remember, our function y to the power of 3 over 2, that is our original f prime, or f at x. So I'm actually just going to derive that to start. That will be what this is. Because y, we've set equal to our g at x right now. We know y is technically equal to the g at x part of our equation. So if I derive that part of the function, we end up with 3 over 2 x to the half. We know that rule. Okay? So think of that part as being the f prime g at x. That's what this is here. And then we have to multiply by g prime x. Well, g prime x is the derivative of the numbers inside. Well, the numbers inside become 2x plus 1 when we derive them. Okay? Oh, that's not what I wanted. There we go. If you notice, this is very, very similar to our... Sorry. Again, this is a y. That's not an x. That's a y. This is very similar to our power of a function rule. The y technically represents x squared plus x. Okay? So what I can do now is I can substitute back in case I was going to get confused at any point. This becomes 3 over 2. We're still left with our x squared plus x to the power of a half multiplied by 2x plus 1. I've substituted that value back in case I was not able to see the original f at x outside function. Now many of you will be able to see that, and you'll be able to jump from this step here right down to here, which is fine. But I want to break it up for you guys so that you guys notice that there is technically two separate functions here. And the next one we'll go is a little more complex. It is more of a function rather than an exponent of a function. But I just wanted you guys to take a look at that. That is technically our function right there, or our derivative. That's our h prime x. And if they wanted us to find the value of it, we could technically just plug it directly into that there.